I'm Peak. I'm RSI 04. And today I'm here to talk to you about parallelism. In particular, how embracing parallelism can expand the horizon of possibilities. And in the story I'm about to tell you, you can in fact see parallelism exhibit itself on several different levels. So let's talk about Alice, a little old lady, who unfortunately has a problem with a long-time loyal companion. No, it's not what you're thinking. It's not her husband. In fact, it's a massively parallel machine that is her brain. Unfortunately, she suffers from aneurysm. What aneurysm is that when part of the blood vessel becomes weakened, and the blood pressure causes that portion to balloon out into an extrusion. Should that not be detected and treated in time, then that could eventually rupture, often with fatal consequences. Luckily for Alice, it was detected early in her case, and she was referred to a brain surgeon, let's call him Bob, who specializes in a form of brain surgery called microcatheterization. In this case, a thin filament is fed through the leg, through the blood vessel system, to go ahead and fill up said extrusion. Once you fill up the extrusion, then blood stops flowing to the extrusion, thus preventing the possibilities of a future rupture. So Bob went ahead and did this, and went home content that he did a great job. However, 2 days later, he got a frantic call from Alice. "Doc, I can't feel my legs." With a sinking feeling, he told her to come in immediately and see what's wrong. So he imaged her brain, and what he saw confirmed his worst suspicions, which is that on the left, you see a healthy brain in terms of blood vessel flow, and you can see that on the right-hand side, which is what Alice was exhibiting, was in fact that no blood was flowing down those vessels. This is something called a delayed branch occlusion. Essentially, during surgery, occasionally things like clots will become loose and then get stuck in downstream brain blood vessels, thus causing loss in brain function. So being the expert surgeon that he is, Bob rapidly figured out, oh, it must be this area of the brain. And then so he opened it up and fixed the problem for her. However, wouldn't it have been so much nicer if he was able to do so during surgery to prevent any loss at all in brain function? In order to do this, let's take a look at what the operating room setup is like for brain surgery. So here you see the physician operating on the patient, and in front of him is actually a series of monitors. Let's zoom in a little further on the monitors. What's displayed on the monitors is in fact a 2D time series of the projections from the front and side respectively of how the blood vessel is flowing through the system. Based upon this, the physician is essentially able to figure out, oh, how is that getting to the patient? Essentially, is using his own prior knowledge of the blood vessel structure of the brain, the static 3D part, as well as a dynamic 2D time series, and essentially attempting a 3D plus time reconstruction mentally during the course of the surgery. Now, our brain surgeons happen to be very brilliant people. Nevertheless, you have to admit there's a certain amount of cognitive load that comes with having to do this projection math in your head. So, in terms of a way of preventing errors during surgery, here is where we can potentially have an opportunity for parallelism. In fact, some systems do exist. You have these big, expensive machines that they produce, which actually generate these 3D time series. What they do is, in fact, quite a brute force approach, where they essentially rotate at all angles and take a lot of shots rapidly of the patient, matching the refresh rate of these 2D systems. Although that does come with a drawback, which means that the patient is eating about an order of magnitude more radiation from said imaging process. Furthermore, it requires a special contrast stat to be injected into the veins, which in fact causes kidney damage. And on top of that, this machine is actually rather expensive. It costs somewhere in the ballpark of $1 million to $1.5 million. So, in this particular case, do we have another way? If you just take a couple of steps away from the operating room, in fact, you'll notice in the next room, there are a number of computers. perhaps that could be helpful. Can we build a technological solution? Here's a surgeon friend of ours who was actually pondering that very problem. When he ended up having a serendipitous conversation with a research scientist from my lab. And the research scientist and him started talking, and very soon they started working together in parallel. In this particular case, the research scientist realized this is a general form of essentially minimizing energy functional through a technique called simultaneous segmentation and smoothing. Essentially, you have a bunch of Euler-Lagrange equations, which you discretize and solve iteratively, resulting in this spatial temporal formulation. Essentially, you try to generate this 3D plus t model. You project it down to the various 2D plus t's. You compare, take the difference, back project it into it, and then enforce various property constraints, like the fact that, all of it has to be inside the blood vessel. It needs to show both spatial and temporal smoothness. So that was an important part of building a solution. Now, I forgot to mention one part. Not only do we want it to have no additional impact on patient in terms of health risks, and have it operate rather cheaply if possible, we also would like minimal disruptions to the surgical process. And so here's where the constraint of less than 5 minutes comes in, because that's the magical time in terms of about how long it takes for the surgeon to change out of surgical garbs and come into this next room to take a look at it. So if we can do that, it would appear nigh instantaneous. So it's during the course of this that another serendipitous conversation happened. I ran into the research scientist in my lab, and we happened to have a little talk about this challenging goal that we're trying to meet. So I ended up taking a look. He had a grad student working for him at the time who managed to produce some highly optimized code, including on the CPU, essentially squeezing every drop of performance you can. And then using this on a rather powerful quad-core CPU, the time ended up a little less than 9 hours. We can't quite keep the patient open for that long. So I realized that I have my work cut out for me. All right, so being an engineer, best type of solution might be brute force. All right, how about we use a supercomputer? When we suggested that to the surgeon, he reminded us kindly that there was that cost factor. It didn't do him any good to spend $1 million instead on servers instead of the machine. At this point, actually Craig himself, one of his quotes is quite interesting, that a supercomputer is a device that turns compute-bound problems into I/O-bound problems. So at this point, I decided to think, what other supercomputers can we think of? How about GPUs? Colloquially known as video cards. So thanks to the popularity of the gaming industry, these things are amazingly cheap and accessible. You can go into any electronics retailer, plunk down about $100 or so, and come up with something that's highly performant. How performant? Something like in the ballpark of an order of magnitude more computational performance. Here I'm listing a mid-range GPU to a mid-high range CPU at the time. You can see there's a factor of about 20 speed up in terms of computational speed. So how much work it's capable of performing. In terms of the memory bandwidth, which is another part, remember Craig's quote about I/O-bound problems? It's the part of the communication, getting the relevant information to the right place for the work to be done. That's only about a factor of 2. And in fact, in both cases, you see a significant drop-off once you ended up hitting the external memory. And then the internal memory, however, on the GPU is much more limited relative to the CPU. So given these challenges, in fact, since it's I/O-bound, we only really want to think about how much time it takes to shuffle the data around. So if you draw out a little graph, you realize that, just to visualize some of what it was earlier, is that at the beginning, the data transfer time doesn't increase very fast because it's the fast internal one. But once you hit that memory limit, now it spikes dramatically. So one key part is taking advantage of it and making sure that you stay within that data limit. Now, I've actually presented a rather simplified model of this whole thing, of the 2-tiered memory architecture, internal versus external. In fact, inside the GPU itself, there's a 4-tier memory architecture And then if you carefully manipulate it and squeeze things into the right amount in each tier, you actually gain a huge amount of performance out of it. Luckily for us, our data is sparse. Out of the entire brain volume, only a small part of it actually belongs to the blood vessels themselves. And what it translates to is about 14% of the rays in the projection actually pass through anything interesting, and only about 0.5% of the voxels themselves. If you translate that into data structures, we go from 800 megs or so of data, which would cause that expensive thrashing out the external memory, down to only 5, which allows us to actually build all kinds of auxiliary data structures to speed up every single part of that computation. Well, at this point, you may be asking, all right, that's great, but how do we do? So let's see. Here is actually a comparison of a mid-range CPU against the GPU. We have 3 rows here: the CPU implementation, a naive GPU implementation, which is standard techniques in terms of state of the art, and a GPU implementation that took advantage of these sparse properties. You'll see that on various portions, we get something like 2 orders of magnitude speed up. On select portions, 3 orders of magnitude speed up. Overall, we get roughly 250 times the performance. And we, in fact, met our goal at roughly 2 minutes. Now, in terms of if you ended up taking back the entry-level dual-core CPU and the top-of-the-line GPU at the time, you will see an even more dramatic speed up. Somewhere goes from roughly 22 hours down to less than a minute. And it's not only the speed up that's interesting in terms of 3 orders of magnitude performance boost, it's also the cost. This is about $100 versus $1 million. That's 4 orders of magnitude in terms of democratizing the accessibility of this technology. Okay, so let's look at some of the impact also. So here is what the surgeon would have to work with otherwise. These 2 static views of the front and lateral. Now we open it up to have them be able to look at it from any perspective at all. Here are just 2 novel perspectives we generated. Similarly, here is across time. Can we have more effective visualization? Sure, we can roughly do a time of arrival visualization. So in this particular case, it's color-coded by how soon the blood flow arrives at a particular location. And on the left-hand side is a normal patient. On the right-hand side is when there's a clot present. By just glancing at it visually, you can quickly determine that the left branch, in fact, gets the blood much slower, and therefore there's probably a clot there. And in terms of the above 2 visualizations, we can in fact combine these 2 into a single one. Let me play some video here. Here is in fact the time of arrival graph, color-coded, and you can rotate it to see this from every single perspective. So just to recap a little bit in terms of the parallelism that we exhibited here. What happens when a massively parallel system goes wrong, in this case the brain? We fix it through a parallel process of a human-computer cooperation, 1/2 of which is a massively parallel computer, the GPU. And then finally, perhaps most importantly of all, this was done by a team, interdisciplinary team, working in parallel to essentially conceive of, design, and build this entire system. So we were able to make that surgeon's dream a reality. And so I guess to conclude, by embracing parallelism in this aspect, by talking to people regularly outside of your normal field of expertise, you're able to get the information to the right place and thus greatly expand the realm of possibility. That's my thought. Thank you.